Hey all dear students, welcome to the Quantum Guru. Let's see this question number 3.32 of Irodov from electrodynamics. The question states, find the electric field potential and its strength at the center of a hemisphere of radius r charged uniformly with surface charge sigma. So this is a hollow hemisphere uniformly charged with surface charge density sigma. O is the center. Z direction is the direction perpendicular to the flat part of hemisphere. R is radius. You have to find electric field and potential at the center. Calculation of potential is very straightforward. Take any element at the surface of hemisphere. Suppose that element has a charge dq. This element would be at a distance equal to radius r of the hemisphere. So potential at center because of this element would be dv is equal to k dq by r. So total potential at the center is the scalar integration, scalar sum of this thing. So net potential at O would be this integration. All elements are at the same distance because after all elements at the surface of a sphere and the surface of a sphere or hemisphere are at the same distance from the center. So this k by r is a constant for that integration. It will go outside. And now the integration of dq will be the total q. So this integration will be simply k total q by r. And q is the total charge of the hollow hemisphere. So now let me put the value of q first, k first. This is 1 upon 4 pi epsilon naught. Q is sigma into surface area, which is 2 pi r square, and then divided by r. So now V will be, just make this pi, 2 pi and 4 pi here, that will be 2. So this V is sigma r by 2 epsilon naught. This is potential. Now for the calculation of electric field, we have to divide this hemisphere into suitable elements. And the suitable elements would be what? Rings, because it is a hollow hemisphere. If had it been a solid hemisphere, the element would have been the disk. So suppose such an element is this. This is a ring wrapped over the hemisphere, or you can better say kind of a ribbons wrapped over this hemisphere. Oh, this is one element. My variable is theta. So this part of the ring is at angular position theta, and this, because of ring has a certain width, and this part of the ring is at angular position theta plus d theta. This angle is with respect to z direction. So this ring has a width. This width would be how much? This width would be r d theta. And radius of this ring is, the radius of the hemisphere is r. So this radius is r sine theta. So I want to calculate first the charge on this ring. Suppose this ring has a charge, say dq. So this dq would be sigma surface charge density into area. The area of the ring, you just cut this ring and straighten the ring. The length of the ring will be 2 pi r sine theta and the width is r d theta. So the charge on this element ring is sigma into area, and area is 2 pi r sine theta multiplied by r d theta. So that is sigma 2 pi r square sine theta d theta. And as my theta will go from 0 to 90 or pi by 2 radian, such rings will span the whole hemisphere. It will cover whole hemisphere. Because of this ring, I have to find electric field at O, and for that thing, I need to recall the electric field due to a charge ring at its axial point. So suppose this is a ring, has a charge q, and this is a point on the axis. Let me draw it a little better. Suppose this distance is, say, z, and any point of the ring is, say, at a distance r from that point. So electric field here, if the q is uniformly charged, is along the radial direction, is along the axial direction, and this electric field is given by kq into z divided by this r cube. And remember, what is this r? This small r is the distance of any point of the periphery of the ring to that point of the axis where we want to find the electric field. So this is the formula I'll be using. So same here, this is a ring, and this point is a point of this line is an axial line for this ring. This is the center of the ring, and here I have to find electric field. So this is suppose z, and electric field will be, because of this ring, electric field will be in the away direction if it is a positive charge. So if I draw the electric line here, so it would be, because of this element, electric field would be like this dE. And now magnitude of dE would be how much? K dq, distance of the center of the ring to that point, that is a z, and divided by distance of any point of the periphery to this point, and that is r cube. This is r cube. Just let me put the values of all these things. K is a 1 over 4 pi epsilon naught. dq we have calculated here. And see also, this z is equal to r cos theta. So this dq into z will make it sigma 2 pi r square, and there I have to multiply by r cos theta. So 2 pi r cube sin theta cos theta d theta. In the denominator, there is r cube. So this r cube gets cancelled. And I want to use this 2 sin theta into cos theta as a sin 2 theta. So this pi will get cancelled. Oh, that would be how much? Sigma upon 4 epsilon naught. And here sin 2 theta d theta. That's all set up. All elements that we will take will have the electric field along the same direction. So direction wise everything is there. So we have to make a simple integration. So net electric field is the integration of this. And this integration, as I told, will go from 0 to pi by 2. So this integration will go from 0 to pi by 2. And that integration is going to be sigma upon 4 epsilon naught, and the sin 2 theta integration is minus cos 2 theta divided by 2. Put the lower limit, upper limit, 0 to pi by 2. When we will put upper limit cos 2 pi by 2, that will be cos pi minus 1, and lower limit 1. So minus 1 is 2, and there is minus, so that whole thing you will get this whole thing, we are going to get 1. So the net electric field, we will get sigma upon 4 epsilon naught. And it is in the negative z direction, the direction that I have chosen. So below z, in the negative z direction. So I should write minus k cap. And that is what we have obtained. Thank you.